Hello all, this is Mohammad Sultan. I'll be presenting today the reachable set of a drone exploring the position isochrones for a quadcopter. I want to thank Daniel, Bernard, and Dr. Becker for their support in this work. If you know the position, velocity, and orientation of a quadcopter, can you predict where it will be next? Better yet, can you predict all possible places it could be in, say, 1 second? That's exactly what we solve in our paper. Our contribution is to calculate the set of all position state reachable by the quadcopter at time t. These plots use equal time contours to show the reachable set. These contours are called isochrones. This set is useful for many applications, including a drone seeking to escape a region in minimum time. This drone wants to escape the black rectangle, which represents the field of view of an HD camera. The drone can escape in 2.12 seconds. In our second example, the drone starts with velocity 70 meters per second in x direction and 15 meters per second in z direction. In this case, the optimal escape is to fly at maximum velocity to the right, escaping in 2.11 seconds. If you are flying a drone around drones controlled by others, knowing the isochrones enables planning for collision avoidance. Here we know the trajectory of our drone, but not the future path of the uncontrolled drone. The first possible collision is at 1.19 seconds. Collision avoidance is the second application for our paper. Knowing the reachable set is also useful for drone countermeasures, such as capturing or destroying a rogue drone. These are the three applications we use in our paper. Now, let us start with the theory. A drone system is a complicated system. It is a 3D model and it has 12 state variables. In our paper, we used 2D simplified model, which explained on Robin Reed's paper. This model has 5 quadrilateral steps, and it has two non-dimensionalized control inputs. UT controls the thrust, UR controls the rotational rate. This simplified system is a dimensionless system. It has x hat, z hat instead of x and z, and it has ut, ur instead of f the force and omega the rotational rate. And these are the equation for the dimensionless dynamic system. Also, ut is constrained between the minimum thrust umin and the maximum thrust umax. But the principle of optimality shows that the optimal controller is always either umin or umax. And in the same way, optimal UR values are always either -1, 0, or 1. Our candidate optimal solutions have two switching times. 1. Thrust switching time TT hat. The drone moves with minimum thrust when T hat less than TT hat, and with maximum thrust when T hat greater than TT hat. 2. Rotation switching time TR hat. If the system is CS, the drone rotates clockwise when T hat less than TR hat, and moves straight when T hat greater than TR hat. If the system is CC, the drone rotates clockwise when T hat less than TR hat, and rotates counterclockwise when T hat greater than TR hat. Here we are showing one candidate solution when the drone moves with full thrust always and TR hat varies from 0 to T hat while T hat is 8.99. In the left is the reachable set and the configuration space is in the right. Both have T hat equal 10 and the minimum thrust is 0.102 and the maximum thrust is 2.04. The blue line is when the drone moves in full thrust always. The green line is when the drone moves with minimum thrust always. The magenta line is when the drone moves straight always. The brown line is when the drone rotates always. And the red line when the drone moves with minimum thrust until T hat equals TR hat minus pi over 2. Then it moves with full thrust. In this slide, we are showing the demonstration that we created in Mathematica to show how changing the minimum thrust and the maximum thrust will affect the reachable set. The black dashed line is the trajectory for the drone from the origin to the final location. Also, this demonstration showing how changing TT hat and TR hat change the drone final location and final orientation. Please feel free to go to this link and discover the reachable set for a drone in this specific time t. Here we are showing the reachable set when the minimum thrust is 4 and the maximum thrust is 4.5 for both CS and CC cases. Points 1 to 4 show the drone trajectories for the CS case for different TR hat and TT hat values, while points 5 to 8 show the drone trajectories for the CC case for different TR hat and TT hat values. Knowing that the yellow regions are reached by input sequences that are not candidate optimal controls, the yellow region spans between the CC and CS sets. When the minimum thrust is equal to 0, then CC included in CS for all t values as shown in the plots. When the minimum thrust is not equal to 0, then CS upper bounds the reachable set and CC underbounds the reachable set, as here the minimum thrust equals to 1.5. To convert to 3D, we will need to rotate about the z-axis as shown in this slide. In the left is the 2D reachable set when the minimum thrust is 0 and the maximum thrust is 2.04, and initial orientation is pi over 3 at t hat equals 10. And on the right is 3D reachable set for it. If the drone starts with initial velocity v0 and orientation theta naught, what will be the reachable set? The reachable set will be shifted in the x-axis and the z-axis by vx0 t hat and vz0 t hat respectively, with orientation theta naught around vx0 t hat, vz0 t hat minus t hat square over 2, as shown in the plot on the right. Negative t hat square over 2 is the non-dimensionalized gravity factor. As you see in this slide, if the drone has initial velocities 5 in the x-hat axis and 20 in the z-hat axis, the reachable set will move 50 units in the x-hat axis and 200 units in the z-hat axis. Here, if the drone has initial orientation 30 degrees, the reachable set will be shifted 30 degrees around 0, -50. This slide shows the reachable set with different initial orientation. All what we did was in the dimensionless coordinates. To transform back to the dimension coordinates, we need to use these equations. Here also, we are showing the reachable set for a drone in the dimensionless coordinates when t hat equals 10, and in the dimension coordinates when t equals 1 second. In our paper, we found the maximum inscribed circle in green and the minimum circumscribed circle in blue that surrounds the reachable set. For the maximum inscribed circle, we solved numerically when t hat less than 2 over 3 pi, and we solved analytically when t hat greater than 2 over 3 pi. And the analytical equations for t hat greater than 2 over 3 pi are in the red box. For the minimum circumscribed circle, we solved numerically when t hat less than 3 over 2 pi, and solved analytically when t hat greater than 3 over 2 pi, and the analytical equations are in the red box. This plot shows r hat versus t hat in the dimensionless coordinates for both the inscribed and circumscribed circles. This plot shows r in meter versus t in seconds in the dimension coordinates for both the inscribed and circumscribed circles. Both fit lines have quadratic growth, and the separation is dominated by a linear term. For the experiment, we used a Hoppy grid quadcopter and recorded the path with different control inputs. The composite image in the left shows that the drone in both modes matches the predicted isochron produced by the reachable set in the right. For future work, we will study the addition of terminal velocity in the model and how that will affect the reachable set. Also, we will examine the 3D xz theta reachable sets, and we'll extend the experimental results with physical quadcopters. Also, we will use the reachable set for drone flight control applications. To conclude, we showed the 2D reachable set regardless of the initial conditions. Also, we showed how to convert from 2D to 3D. And we presented the three applications that our paper can be used for: collision avoidance, escaping from a camera view, and drone countermeasures. Last but not least, we showed that the experiment matches the theory.